Good afternoon, everyone. Today is our first international webinar with a special guest, Professor Arben Merkoçi from the Catalan Institute of Nanoscience and Nanotechnology in Spain. It is my pleasure to introduce Professor Arben for you all. So Professor Arben is from Albania. He obtained his PhD at the University of Tirana in Albania. He carried out research as a postdoctoral fellow and research professor at the Polytechnic University of Budapest, Hungary, University of Ioannina, Greece, Università degli Studi di Padova, Italy, Universitat Politecnica di Catalunya, Universitat Autônoma de Barcelona, and New Mexico State University, USA. His research is focused on the integration of biological molecules and other species with micro and nanostructures to develop novel biosensors and sensors. Professor Arben is co-editor-in-chief of Biosensors and Bioelectronics, the principal international journal devoted to research, design, development, and application of biosensors and bioelectronics. He's also a member of editorial board of Electroanalysis, Microquímica Acta, and other journals. So after this brief description and introduction, I'm gonna call Professor Arben here to the stage, the main stage. So, hi Arben, we are on live. Hi, it's a pleasure. It's a pleasure to have you here with us. So if you can start, I'm gonna include your screen on our screen. So let me.
Okay, can you see my screen?
Yes, we can see, yes.
Okay,
so
okay.
It's over to you now.
Okay, thank you very much, Livia. Thank you very much for the nice introduction, and thank you very much for the invitation, you and the colleagues from IQ-UFG. And it's a pleasure for me to be today with you, with colleagues in Brazil, beautiful Brazil. I have been several times, but since COVID I have not turned back. I wish I'll come again because I miss my colleagues, collaborators. Lydia was one of them, but I would say there are a lot of colleagues and friends in Brazil who have been working in Barcelona with us, so it would be a great pleasure to come again in Brazil. So today I'm going to speak about nanobiosensors we are developing in Barcelona. We call these sustainable biosensors because we are trying to use simple materials. In addition, we are trying to develop techniques and integrated system in which these sensors can be useful, connected with interest for different applications in diagnostics. And when I say diagnostics, I mean health, but also environmental monitoring. First, let me show you a little bit about this presentation. I will go briefly about ICN2, the Catalan Institute of Nanoscience and Nanotechnology, where I work, and my group, what we are doing. Then I'll speak a little bit about health, for example, as one of the most important applications, and point-of-care systems, and in this context about nanobiosensors. And then I'll give you some examples of optical sensors, electrochemical sensors that we are developing. So, as I mentioned, I work at Catalan Institute of Nanoscience and Nanotechnology. This is a joint research center. This is why you see different logos here. This center is situated in Beaterra. This is a very nice area. As you can see here, this is the campus of Autonomous University of Barcelona, where our center is here. We have also other centers in the campus, like material science, microelectronics. We have synchrotron here. And you see here behind this mountain is the city of Barcelona. In this campus, we have a cluster of around 750 scientists working in the area of micro nanotechnologies with interest for different applications. And in our center, we are working in the frontier of science, in the frontier of nanoscience and nanotechnology, trying to develop different technologies related to nano and nanotechnology, nanoscience, and also trying to do innovation and also training of next generation of scientists. So in our center, we work not only in the basic science, so trying to understand fundamental basics of nanoscience and nanotechnology, but also we have a lot of interest in transference of technologies and also the dialogue between researchers and society, which is very, very important, and also training of next generation of scientists. In our center, we work in different areas, as you can see here, from bio, environment, energy, health, quantum, fundamental aspects of nanoscience and nanotechnology, electronics, going from manipulation at atomic molecular scale, characterization, fundamentals, exploitation of functionalities of nanomaterials, to the design and application of devices based on our structures for different applications. We have different research groups in our center, as you can see here, in different areas, in nanoscale manipulation and characterization, nano-device fabrication, physical properties, theory and simulation, chemical rules and nanostructures, and together with several colleagues, we work also in the area of nanobiointerfaces and devices. So in addition, we are part of Barcelona Institute of Science and Technology. This is why you see also this logo, in which ICN2 is together with 6 other excellent research centers of Barcelona, working in different areas, such as, for example, optics, chemistry, energy, and more. Now entering in what our group is doing, nanobioelectronics and biosensors. Our group is focused in the discovery and technological development of cutting-edge nanotechnology and nanomaterials. We are trying to use a different kind of nanomaterials, different kind of exploiting different kinds of phenomena with interest for sensing and biosensing applications. So you can see here different kinds of nanomaterials, from metallic nanoparticles, nanopores, graphene, nanotubes, quantum dots, and more, and trying to apply these in biosensing system in different areas that goes from diagnostic, environmental monitoring, food quality, safety and security, in addition to other industrial applications. In addition, we are interested in technology transfer, and this is why from our group we have 2 spin-off companies, Paperdrop and Graphenical Lab. Paperdrop devoted to paper-based sensors for diagnostic, and Graphenical Lab to graphene patterning with interest for electronic devices. And here you see several kinds of devices. I will explain in the next slides, in which we are trying to apply different kinds of platforms, usually paper, plastics, and integrate nanomaterials with interest for sensors and biosensors. So, as I mentioned, so we have interest in nanomaterials, we have interest in platforms like paper. You can see here, for example, paper-based sensors like lateral flow, but also full integrated system, including smartphone connection, using different printing technologies, inkjet printing, screen printing, stamping of electrodes, etc., with interest for different kinds of applications. So let me now enter in the topic, health and point-of-care devices, health, but also environmental monitoring, I would say. But first, a few words about biosensors. Most of you know about biosensors. I just put here a typical example similar to glucose biosensor that you may know, and it is in any pharmacy in the world. A biosensor is similar with, for example, a glucose biosensor in which you have a disposable part and this tiny instrument to read the signal. This tiny part, so this disposable part that is the biosensor, is where we have the receptor and transducer. And depending on the kind of receptor you are using, either enzyme, antibody, DNA, or aptamer, and the kind of transducer, depending on the transform of the signal that you are getting during the interaction of nanolight with the receptor, you may have either change of the current, so you have electrochemical biosensors, you may have change of the light, optical biosensor, or even change of the mass. So the possibilities for this kind of biosensors are enormous. You may have different kinds of biosensors depending on these combinations of electrical enzymatic biosensors, immunosensors, etc., etc. And of course, different kinds of configurations that goes from wearables, smart packaging for food control, implanted devices, in vivo formats, and more. So nanomaterials that we are working with, being in the center of nanotechnology, as you know, are very, very interesting materials. They have sizes that goes from 1 to 100 nanometer, and the different kind of nanomaterials that I mentioned also before curiously fit quite well in terms of size with different molecules, for example, with glucose, protein, DNA, or even a virus. So, and it is normal for nanomaterials to work together with these biomolecules or even virus or bacteria because of the size, but also because of the different advantages, properties of nanomaterials. There are large surface to volume ratio, their shape, physical mechanical properties, binding properties, make this nanomaterial very, very interesting while being applied in building new biosensors or improving the existing ones with interest for different applications. Biosensors nowadays can be everywhere. You can have biosensors as medical devices, as wearables, as smartphones. Smart TVs also are trying to integrate sensors with interest for even to be used at home. Everything you see smart, smart fridges, smart washing machine, smart houses, food plant control, environmental control. So the smart cities in the future indeed are going to request the use of sensors and biosensors. You cannot take any measurements, you cannot follow any quality, for example, of the air, quality of the water, or even the health monitoring without sensors and biosensors. So these are going to emerge more and more in the future while building the cities of the future. So biosensors can be integrated very easily to smartphones. Indeed, everyone has a smartphone, as you can see here. It is easy to be converted a smartphone to a biosensor. Here you can see, for example, a biosensor connected to a lateral flow, or a biosensor connected to a microscope, or even other different connections, for example, with microfluidics. The interesting application is here with this Google Glass. We see this guy is reading a lateral flow, and these Google Glass are capturing the image, are treating the image, and then converting the image to some quantified values, for example, of concentration. It even could be a COVID present, etc., and transmitting these through Google Glass to the medical doctor office and take some decisions. So the biosensor market is huge. Just in the United States, you see these numbers, different kind of biosensors. The market is increasing, being the market of electrical sensors, for example, very huge in comparison to other sensors. So it's a matter of technology. And the substrates to build this kind of sensors may be different. So we are very much interested in sustainable sensors, so using paper, for example, but also flexible substrates, plastics, with interest a lot in low-cost, abundant material like paper, which is easy to manufacture, recyclable, sustainable. You can also in the paper integrate microfluidics because based on porosity, you can have through the capillarity forces liquid to run without the need for any pumping system. So it's a kind of zero energy device. But for these sensors to be integrated and to be used as biosensors as point of care, they need to be reassured. It means real-time connectivity should be there, easy of specimen collection. This should be affordable, sensitive, specific, user-friendly, rapid and robust, equipment-free, and delivered. Of course, sometimes you cannot fulfill all the requisites, but it's important to keep this in mind while building your sensors. And these kind of sensors we are developing are very, very interesting. Of course, we can integrate metallic nanoparticles, we can integrate graphene, different kind of receptors, taking advantages of properties such as plasmonic of nanoparticles, electrocatalytic properties of nanomaterials, conductive nanoinks, but also different kinds of bioreceptors, including DNA, antamers, and more. And the kind of reading we are doing is either naked eye, but also we are connecting with smartphone. We are building portable readers with interest for different kinds of applications. So there are a lot of challenges while building this kind of devices. Sometimes we need these devices to be completely non-invasive. We want these to be real-time monitoring capability, to have. We also want sometimes to generate biodata, big of data, for example, in applications related to artificial intelligence with interest for this kind of devices. We want also sometimes to have cheap, low-code devices, but also to correlate data, to get insights about the body. And all these issues, these are very, very challenging for different kinds of applications. So nanobiosensors we are developing in the laboratory, as I mentioned, as a summary, are based on nanomaterials with different kinds of readout, with different kinds of substrates, and I will show you different kinds of applications that go from health, like for example, neurodegenerative disease, but also environmental monitoring with interest for different areas, as you see. Here are some of the papers, but I'm going to explain some of them that are showing different kinds of devices with interest for different applications. But why we need fast and efficient diagnostics? And we say diagnostic not only health, but also environmental monitoring. So COVID-19 was a tremendous real-world example, showing the need for efficient diagnostics for the protection of us all. So we are living this pandemic during almost 2 years. This is the first year we are out of these pandemics. But during these pandemics, you know what happens, so the impact in terms of people infected, in terms of those who lost their life. So diagnostic tools have been crucial because we couldn't take any decision to protect our life without the use of biosensors. But during COVID-19, we have learned also a lot, and during this period, we wrote this interesting review in ACS Nano, in which we showed that the development of new diagnostic device is a process characterized by several bottlenecks, and most of them are related to suboptimal interaction between actors involved, like scientists, clinics, regulatory bodies, and the companies. So, to do a development of sensors, it's very, very important to connect the science with business. So, in terms of all the developments of the TRL, MTRL level, from the very low to the very high. So, from the conception of the design to laboratory testing, clinical trials, the regulatory review to scale up and launch. So, it is very important, and it's crucial for the devices we're developing to keep in mind this collaboration and the way how we increase this TRL. You have more information, and with some examples in this review, if you want to read more. So what is interesting for us is the ubiquitous fabrication of nanobiosensors. So nowadays, nanobiosensors are produced mostly in the clean room. So usually these are centralized production facilities. But what about going from decentralized fabrication to ubiquitous fabrication of nanobiosensors using simple printing? So centralized versus ubiquitous means that instead of delivering the devices from these big fabrication facilities to any country in need, why not to distribute the fabrication facility so with simple printers to everywhere? So in the case of emergency, you can print this kind of sensors very, very fast. You can give response to the emergencies in your country, and you don't need to wait by sensors with all the delay that you have in these cases. So this is very, very important. So democratized diagnostics means these ubiquitous diagnostics that can be done thanks to these innovative nanomaterials and nanotechnologies. There is a simple and easy production of nanomaterials that coming their modification with receptors, low cost scalability of the production of these biosensors, portability, sensitivity and reproducibility, equipment-free capability of these devices, which is really very, very important. So for this reason, we are working since years, and recently we got a very interesting project that's collaboration between different countries, so trying to help and to boost the research capability. For example, from our university in Albania, my origin country, that have low resources and the need to boost the research capability, and we are trying to transfer there our knowledge and technologies so as to build in collaboration with our partners in Olomouc, so the two research centers in Europe, excellent centers trying to collaborate with the University of Tirana in terms of producing and applying sensors based on graphene for environmental monitoring. So let me show you some of the examples based on this concept. So some simple optical sensors we are developing, and then some electrical sensors. Trying with optical sensors, you all know that optical sensors are various. You have magnetic, fluorescent, electrochromic, evolution. There are different kinds of optical systems. I'll show you some of them that we have been developing since many years. First of all, with lateral flow sensors, this has been one of the most important devices during the pandemics, and this is why we wrote these nature protocols with the idea to teach to all the community how to build, how to design, and how to fabricate a nanoparticle-based lateral flow immunoassay. This was the kit that was used, the fast device for COVID detection. You can use any kind of nanoparticle, and this review showed that, for example, you can use gold nanoparticles, carbon nanoparticles, magnetic nanoparticles, quantum dots, liposomes, and more. We show in this review how you can build your lateral flow from the assay design to the preparation of all the components of the assay, from nanoparticles and modification, how you can prepare the conjugation path, how you treat the membrane, and how you produce all the setup going to the reading that can be either by daytime, but also by the use of readers, including a smartphone. So we have a lot of information in this nature protocol. This is now one of the examples I want to show you based on the use of graphene. This is based on the quenching capability that graphene oxide has toward quantum dots. You can see here this bacteria is captured by these quantum dots modified with antibodies, and graphene oxide is coming due to some electrostatic interaction and quenching the graphene quantum dots, cadmium selenide. Let me show you this video that shows how this device works, how simple it is to produce this paper-based sensor using lateral flow. So first of all, we set up the paper-based sensor. So we need to cut the paper, use laser now, not this graphene. But you can see the paper with different velocity are set up. Afterwards, we use cadmium selenide quantum dots. So this is cadmium selenide here producing. And afterwards, we excite these quantum dots with UV visible light. So you see after the excitation, you can see the photoluminescence coming from these quantum dots. Afterwards, we use the graphene oxide suspension, and due to the interaction of graphene oxide with these quantum dots, the light is quenched. So we follow this quenching of the light and correlate this quenching of the light with the presence, absence of the bacteria. So this is really very simple. You can imagine that if you change the receptor, you can detect any kind of bacteria. You can also do multi-detection based on what you want to do. And of course, after some optimization, you get the system to work fine. We proved to check also the interferences, for example, toward different pathogens, and we found out the system was working fine. So this kind of system, this kind of biosensors have been applied also by our group in different applications. This is another application in which we use gold nanoparticles and apply this paper-based sensor for the detection of some cancer biomarkers, parathyroid hormone-like hormone, which is of interest for some studies of some drugs of interest to fight the cancer. So here you see the design based on lateral flow, response toward this hormone, and then some quantifications of this hormone based on this lateral flow. So this is a really very, very simple system. We have been working with this also during COVID, and one of the very interesting findings is related to how you bind the system, how you develop your lateral flow, and one of the main issues is to define the affinity of antibodies against, in this case, SARS-CoV-2 related protein, and we found that some of the antibodies that were in the market were not with the right affinity. So it is very, very important to validate first these biomarkers, usually using ELISA, Western blot, but also it's very, very important before using these and setting up the device to have data about this. And we are suggesting that the companies should give this data, the binding kinetics of these receptors, that is very, very important before setting up your device. Otherwise, the devices were going to fail. And this was very, very important. And some conclusions and the way how you define this affinity constant are shown in this large paper. We also have been working with different kinds of nanoparticles. This is a case in which we try to increase the signal by using iridium oxide nanoparticles combined with gold in a way that, as you can see, for example, the standard gold nanoparticle based assay is able to detect up to 10 nanogram per milliliter human IgG, while we go down to 3 nanogram per milliliter in case of using of gold iridium oxide nanoparticles in different concentrations. So this is very, very interesting to get higher sensitivity. Then we have been moving toward improving of lateral flow by combining lateral flow with electrophoresis. And here is the schematic. You see that the lateral flow is connected now to with two electrodes, a negative and positive electrode. So by applying the high voltage using a smartphone, using an inverter and electrophoretic cell, we are able to move the sample and boost the separation. We are able to separate the mixture of different quantum dots. You see here blue, and then we have this blue, red, violet quantum dots. Let me show you the results here. So we have been applying this in the separation of whole blood. You see here, once you apply the voltage, the blood is running, and we are improving. We are having a synergy between the lateral flow separation and electrophoretic separation in a way that we get an improvement of the sensitivity thanks to this combination. We are still working with this and finding that this is very, very interesting while working with very complex samples, matrix, where we have to separate some interference. Also, we can use nanopaper. So this is a transparent paper based on nanocellulose, special cellulose produced by special bacteria, in which we produced different kinds of nanoparticles like silver, gold, quantum dots. You see here, nanopaper is transparent. So after interacting with this nanopaper with different kinds of compounds, for example, with cyanide or some other compounds, you see that the color of the paper is changing. This is because these compounds, for example, cyanide or other compounds, are interacting with the nanoparticles, changing the plasmonic of the paper and making this piece of paper working like a pH paper. So this is really very simple. And combining this with interaction with antibodies, we're able to convert this piece of paper to a selective sensor, for example, to detect pathogens or proteins based on the function capability that now is driving through the specificity, selectivity of antibodies. So we could detect bacteria or even proteins based on this paper. We are also very much interested to integrate this detection system in integrated platforms. This is a case of Alexa system, which is portable and connected to a smartphone, in which we integrated an Alexa placed with stepper motor, temperature, and humidity sensor, and also Bluetooth, Arduino board, emission filters, use also the sample and then the LEDs that are used there to do the measurements in different colors. So here you have some examples of the system applied as NISA for COVID detection, for magnetic detection of COVID using some HRT and TAB diameter measurements or 3D measurements using this NISA system. You see here how it works. You see the system is totally automatic. So once we introduce the plate, the NISA plate, you get the measurements and get this reading that we can do even out of the laboratory. We developed also the app of this smartphone that connect all the different kind of measurements and be able to do any kind of application, the same as you do, for example, when you work with ELISA in the laboratory. These paper-based sensors are now being used by our company. So we have the paper drop who is working in campus, trying to develop adaptive platforms with proprietary technology and also image support and connectivity system with interest for different applications in collaboration with hospitals in Barcelona. Now, in the remaining part of this talk, I'll show you some examples of electrical sensors we are developing. So the electrical sensors are different depending on the transducing system. You may have amperometric, potentiometric, conductometric, EMG-metric, or field effect resistors. So here are some examples that I'll show in the next slides. The one based on the graphene, so transference of graphene and building some electrodes using laser scattering mode. I'll not show some connection with electroluminescent panel, but you can find this in this paper and the other papers that you may ask me also to present to you. First of all, a simple example in which we use the electrical system, in this case hydrogen evolution reaction, that is induced by gold nanoparticles. You know that gold nanoparticles are catalysts for hydrogen evolution reaction, and we use this detection system to detect some Alzheimer biomarkers with interest, for example, to detect this in human samples using magnetic microspheres. So these magnetic microspheres are connected with antibodies against the biomarker. Then we have a secondary antibody that is connected to gold nanoparticles. And afterwards, we measure hydrogen evolution reaction. And you see here the microbeads that we use, and then the measurements done in of this biomarker in different samples, and you can see the response of the system. So in terms of the catalytic current for different concentrations of these biomarkers, included a spike in different standard solutions, CSF, serum, and plasma. So this was very, very interesting for diagnostics of Alzheimer. We also moved toward very sensitive detections of these some proteins, and in this case you see the aptamer-based sensor for the rapid and reagentless detection, quantitative detection of SARS-CoV-2 spike protein. You see this is very, very interesting system in which we have a wire, a gold nanowire, that is modified with an aptamer that is against SARS-CoV-2 spike protein that interact with specifically with this protein. This aptamer is connected with a redox reporter, methylene blue, that you can see upon interaction with the SARS-CoV-2 spike protein, the distance of the redox reporter with the electrode, so in this case the gold wire, is changing, so the transference of electrons is changing, and we see the change of this the signals of the current versus the concentration of this protein. So in different, having the dynamic range, very, very interesting. So having these for different frequencies we have been studying, showing so that this electrochemical sensing based on the binding induced conformational change is really very, very interesting, giving a very, very high sensitive response. We move toward a much more complex system, but very, very interesting, in which we designed the DNA we call this elliptical-shaped scaffold structure, in which we have a recognition structure and two anchoring stand 1 and stand 2 that also can change based on the interaction with the target antibody. Again, we're using this for the detection of some target antibodies as proof of concept. You can see that again, this architected DNA with the redox reporter is changing the conformation, and we can detect the change of the current based on the interaction of this elliptical-shaped DNA with the target antibody. After doing the measurements and controlling native and modular variant with internal control variant, we are able to measure the concentration of the antibody with very, very high sensitivity based on the changes of the signal coming during this interaction of this electrode, the gold electrode used for this case. The sensor was able to give response in around 10 minutes with very, very high specificity, and of course can be extended to many other applications based on proper design and architecture of DNA according to nanolight. So we are trying to plug, print, and play by using inkjet printing, and this is very, very interesting. And this is a case in which we use a smartphone for the detection of NGAL, which is a biomarker of interest for acute kidney infection, with interest for detection of diagnostic of liver cirrhosis. The concept is very simple. So first of all, after doing some simulations for the single nanoparticle-based electrode printing with an office printer, fabrication, and afterwards doing some modification of the surface and connecting their panel against angle, we were able to connect with the smartphone and have this ready for the application. So this is how we use, for example, graphene, which is one of the most important materials we are using for our electrical sensor. We have developed the water activity graphene oxide transfer using wax printed membrane. This is a patented technology in which we use some wax printed membranes in which we can print any kind of shape, filtering the graphene oxide suspension, and after filtration and drying and water activation and fast drying with using pressure, we can print any kind of surface. Of course, we need to characterize first, and then after characterization, we can print any kind of shape, printing electrodes to interest for different applications. You see here, for example, a touch-sensitive device that is turning on and off this LED based on the use of this graphene. And we can print on any kind of surface, pen, textile, paper, adhesive film, and more. This is an application of our graphene-based technique, but now improved by laser scribing, in which we apply the laser in graphene that is embedded with some precursors for different kind of nanoparticles. So now in the surface of graphene we have different kind of nanoparticles, also gold, silver, platinum, depending on the application. Of course, after characterization, we're able to apply this for different applications. For example, here is also another example in which we included some two-dimensional structure. So we combine graphene with these to have a synergy between graphene and these TMDs with interest to improve the electronic transference and have these sensors produced even onto paper with interest for electrochemical application. You see here, for example, the improvement of the system from the graphene to reduce graphene oxide and reduce graphene oxide, including these two-dimensional heterostructures. This is one of another example in which we apply this to detect this graphene, mesocyte graphene to detect bacteria, in which you see that this graphene-based sensor is connected to antibodies that recognize bacteria, and then another antibody connected to enzyme is giving the signal through the interactions between the hydrogen peroxide that is in the medium and the change of the mediator and the electron scatters that goes up and down. measured through using the smartphone. So we were able to detect a very low concentration of bacteria, and of course, comparing this with some possible interference, we were able to show that this system was selective and even stable during the time, up to at least 1 month. Another very interesting system we have been working with is based on wearable. We developed a very simple wearable device in which our sensor connected with the smartphone is operating now to detect heavy metals using electrochemical staining, as you can see here. Here are some details. I'm not going to do these. More details we have in the paper, in which we show that microfluidics, so in this case, the detection of heavy metals in sweat, practically we detected copper ions, which are of interest for diagnostics applications. Here you have some results. Spiking, for example, to detect how the system was responding toward different concentrations of copper, and the response of the system in this case impedance toward these changes of the concentration of the copper ions. We have also applied this system to detect heavy metals in different kinds of samples in collaboration with our partner in Nanoscience, Czech Republic, using some very interesting metal fluid system, motionalized graphene, bringing more selectivity and avoiding the interferences, as you can see here, for example, during the detection of lead, copper, cadmium. You have problem with interferences, but using this metal fluid system, we are increasing the selectivity and the sensitivity of the system. And finally, we applied the system to detect heavy metals in waters. So we integrated this heavy metal detection system in some boats. So after setting up the microfluidic system, in collaboration with our partners, we integrate everything in the boat, and then did some measurements in the boat of different kinds of heavy metals. You can see here cadmium, lead, and copper. And this boat going around that was fabricated by our partners in Italy and other colleagues in different parts of Europe, in which this boat was used to detect heavy metals in different parts of this river, trying to determine some accidental contamination of different kinds of heavy metals. Finally, you will show some more information in the website of our spin-off company, what definitely that was doing. So I'm just skipping this video because you have to internet to get more information about the company. So if you need more information, we wrote these reviews. So you have these reviews also, where you can see different kind of application of nanomaterials for different kind of areas that I mentioned also here. And finally, I'd like to mention that I hopefully transmitted to you the idea of the importance of the use of nanomaterials to build new kind of sensors, sensors for different kind of application, and how to connect these to build sensors that are of interest for health monitoring, environmental monitoring, and different other applications. So, and of course, I'd like to thank all our partners, our sponsors, and collaborators. But overall, I'd like to thank all my collaborators, people who have been doing this work from different parts of the world. Some of them have left, so we have new people, more new people here, but some of them are not now, are in different parts of the world. Some of them are also in Brazil. I'd like to mention also an interesting conference that we are organizing in Tirana, Albania, my origin country. You are invited to come, so it's a big panel of speakers. So if you come there, so just let me know if you would like to participate. It's going to be a very, very important conference. Thank you very much, and if you have any questions, just let me know. Thank you very much.
Thank you, Arben. It was a really interesting talk, very inspiring research. And now, if you want to close your presentation, yes, now you can see us here on the screen.
Yes.
Yes? Okay, so we have some questions here. Let me show. Yes, from Professor Martin. Thank you for your excellent presentation. What are the current challenges for the large-scale adoption of portable biosensors?
Yeah, this is a very important question. So, large-scale production of nanobiosensors is something that we scientists can do it just in collaboration with companies. Because the techniques, fabrication techniques you use in laboratory are for low-scale fabrication, but if you go for large scale, you need to have other kind of fabrication tools, and also you may need to consider other issues that are related to the metrology of the system, nanometrology, also all the chain of the materials you are using, and what happened during the time, during the storage of these materials. So there are a lot of issues. I think this is the best way to do it with collaboration of spin-off companies or industries.
Thanks. I have a question related to this topic as well. Most of electrochemical sensors and biosensors in the market are for glucose detection. Most of them are concentrated in this field, but in the labs, different labs are producing research about different types of electrochemical biosensing, but it's really hard to achieve the market. One of the reasons is the large scale production, but there are other issues as well. So I would like if you could talk about the other issues
Okay.
related to this.
Yeah, this is a very good observation, and I used to say this also to my students. So why we see only the glucose biosensor in the market, and not only the simple glucose biosensor that you take a drop of blood and use this, and you can do it at home. But nowadays you have this wearable glucose biosensor that can, in an automatic way, control the level of glucose, and even more. There is the last generation in which we have this glucose monitoring system, and also the device that inject the insulin. So you have the correction in an automatic way. So all the system, wearable system, is doing measuring of glucose and correction of by injecting insulin. So you can do a totally normal life, for example, during 2 weeks. But why have these devices? We do not have devices that control cancer biomarker, or control, for example, uric acid, or control, for example, some dopamine or whatever other biomarkers. I think the first thing is to close the market. So having a huge market for glucose biosensor, it means that a lot of investment has done in this field. So a lot of companies has worked and have developed a lot this system. So we have this everywhere. So the demand is one of the things, and the investment in the area. And if you go for other applications, then the demand and offer is the problem. Then you should, and of course, these are issues that are not issues that for us as scientists probably is difficult to understand, because we hope to develop cost-efficient devices, but then if you go to the industry, they see this with interest for the market if they can fabricate it. So other issues enter there. So these are very, very important. But I think that other issues that are in addition to the market, which is the most important, and the funding from the industries, I think all these other applications need to be more robust and need to be sensitive enough, and of course free of interferences. And these are, of course, issues that are related to the fulfillment of requirements of the performance. So if you have a device that is working fantastic, very, very well, probably industries would be interested and probably can fabricate your sensor if they see it's with interest for the market. So I mean, there are a lot of issues.
Yes, a lot of issues. Thank you, Arben. Another question, the last one, I think. You talk about the lateral flow devices, and you showed the video about the use of quantum dots instead of gold nanoparticles, right? In comparison to the gold nanoparticles, they are much more sensitive. Yes?
Yeah, quantum dots in principle are more sensitive than gold nanoparticles. It depends, of course, on the quality of the quantum dots, and this is why we have been also working, and also there are people working on quantum dots. So the issue is related to the sensitivity. And sometimes you can do even the multiplexing because you have particles of different colors, so you can have multiplexing, so you can multiplexing things with different parameters, different biomarkers, so also use difference. Yeah.
Okay, Arben, thank you very much. It was a pleasure to have you here with us today, and I hope you can visit us soon in Brazil.
It was a pleasure for me too, and I really wish to visit you and meet in person you and all other colleagues. So, and I wish you all the best and good luck in your research as well. And we are open for collaboration and waiting also for students, postdocs, professors to come in Barcelona. Barcelona is a beautiful city, and I'm sure that the Brazilians will enjoy being working in Barcelona. So, thank you
Yes,
very much.
Barcelona is amazing.
Barcelona is beautiful. So
Beautiful,
Europe
yes.
in general. So as beautiful as Brazil. So
Yes, yes. It's
okay.
two beautiful places. So thank you very much, Arben. Thank you very much, you all that were with us during this webinar. See you next Monday with a new webinar. So see you again. Bye bye.
Bye bye.
Arben, we're gonna come back to the backstage, okay?
Okay.